So in this set of lecture, we are going to discuss about gain compression, 1 dB compression point, intermodulation distortion, third order intercept point, receiver sensitivity, and the receiver dynamic range. So first concept is gain compression. So previously I give you a very simple example in which I just use one resistance just to show you a little bit of what exactly a non-linearity looks like. In this example, we look at a non-linear amplifier, and we are going to discuss about its input and output characteristics. So imagine we have an amplifier as a black box, and we have input voltage and we have output voltage. So what normally an amplifier does, it actually takes in a weak signal and it converts it into a strong signal. So that's the general behavior of an amplifier. Plus and ground. Yeah. So if I plot my V in over V out, generally what happens that for a given value of V in, I will get a given value of V out, that is an amplified value of V out. So as I increase my V in, my V out will also be increasing. But there is a point after that, if I increase the value of my V in, my V out will not increase. So that kind of area will give me a non-linear behavior of this kind of amplifiers. All circuits are non-linear to some extent, therefore they all produce non-linear distortion. So in real systems, this kind of non-linear behavior is kind of catastrophic for my system to work. Non-linear distortion creates unwanted frequencies that interfere with the signal and degrade the performance. So for example, if I have non-linearity involved in multiple amplifiers that are used to define my signal, there is a possibility that they are going to create an interference for another signal or a neighboring signal that I want to transmit through a same device but using a little bit of different frequency or different channel. So the transfer characteristics of an amplifier is a plot of instantaneous output amplitude versus the instantaneous input amplitude. For an ideal amplifier, the output is simply a larger version of input waveform. The output is proportional to the input. So that's what exactly we have seen here, that a simple input curve is kind of amplified at an output of an amplifier, but that's kind of an ideal case. In real life, we face distortion as well. For an ideal amplifier, the transfer characteristics is a straight line whose slope is constant gain. This is also known as small gain. Yeah, this concept is also clear. This concept is also important, that if we look at a small value of V in and a small value of V out, then generally this kind of curve is constant. So that's why we consider these kind of small areas inside on this curve as small signal gains. So if there is a slope that is followed by an amplifier V out or V in curve, then that slope will be small signal gain. That can be different for when the signal is from a very low value of V in to a very high value of V in. But if I take a chunk of that gain spectrum, then I will have small signal gain. However, real amplifier has transfer characteristics that depart from a straight line, particularly at large amplitudes. Gain is no longer constant. So that's also called large signal gain. This is exactly what we have seen in our last slide. Real amplifiers cannot produce output voltage or current beyond certain boundaries or bounds dictated by the electronic device and the power supply. So this is important. This actually the device physics stops a device at a certain point where the input is not equal to output. So for example, if I have V in and V out, and my amplifier is having a pretty nice gain for a given value of V in, it is giving me a very high value of V out. Imagine the scale here is small. For example, this is 2 and this is 6 and this is 12. Then for a gain of for 3, 1 2 3, I am getting 12. For 1, I am getting 6. So the input and output curve is kind of very nice, but at one level after this, if I increase my V into 4, it should get 18, but it gives me, you can say, 13 or 14 or something. Then my output is not increasing as I expected it to increase, because it should amplify, but it is not amplifying. Then I will call it as gain compression. Consequently, the transfer characteristics eventually become non-linear for extreme input values. Curvature of transfer characteristics result in an undesirable effect known as non-linear distortion, that is this area. The output of amplifier becomes saturated at some value as the amplitude of the input signal is increased. So this is also called saturation. You may have already heard about the saturation points and saturation of normal amplifiers. It's exactly the same in high frequency amplifiers. Large signal gain is the gain obtained for an input signal that is strong enough that it affects the operating point, resulting in nonlinear behavior. So large signal is kind of like at from this point to this point, we have a behavior in which my amplifier is just about reaching its area where it is giving me a distortion behavior rather than amplifying my signal nicely. So consider a nonlinear system transfer function model. To understand the nonlinearity, we have to consider a simple transfer function model that has linear plus nonlinear components. So we can define a transfer function y of t of an amplifier almost equal to a1 x of t plus a2 x square of t plus a3 x cube of t. Now xt is a cos omega t. So if I want to draw this a cos omega t, it should look like a simple sine wave, or you can say cos wave, having an amplitude of a. Now there is another factor multiplied by it, that is a1, that kind of gives a linear constant multiplied by a sine wave that is just going to enhance its amplitude. So again we have a2x square of t and a3x cube of t and so on. Let's only consider first three points. So y of t is equal to a1 a cos omega t, and then a2 a square cos square omega t, and a3 a cube cos omega t cube. So we know that a square omega t can be derived from this trigonometric identity, should be equal to cos 2 theta is equal to 2 cos square theta minus 1. Here theta is actually omega t. So if I take this value and put it here and push the other value on the other side, let me try to drive it for you guys. So cos 2 theta should be equal to cos square theta should be equal to cos 2 theta plus 1 divided by 2. Yep, we can push it here as 1 plus cos 2 omega t divided by 2, that comes out of the bracket. Similarly, a3 a cube cos cube omega t can be derived from this trigonometric identity, where we have 4 cos cube theta minus 3 cos theta is equal to cos 3 theta, 3 theta. So just to derive what cos cube theta should be, it should be equal to cos 3 theta plus 3 cos theta whole divided by 4. Again I put this value here and eventually I will get to this equation. Now rearranging some of the points, this factor multiplied by 1 will give me a linear value. This factor multiplied by cos 2 omega t will give me this value. This factor will go, a1 will go here, and this 3a cube over 4 multiplied by cos omega t will go here, and cos omega t is kind of going out of the bracket, and the rest of factors will go here and so on. So here in this equation, this particular portion is of importance because this is the factor that is actually multiplied by cos omega t, and cos omega t is this sine wave that we had talked about at the start of this slide. So there are few observations and few points that we can identify from this equation. If a alpha I is much greater than all the other factors that contain a, then the small signal gain is equal to alpha 1a. So as you know, what was our equation? Let me try to find out what our equation was. Okay, so equation was a1a alpha 1a plus 3 alpha 3 a cube over 4 multiplied by cos omega t. So here this a1 alpha 1a is actually main participant of this first sine wave. So whatever will happen at the output y of t is actually a combination of a DC that has no multiplication with cos omega t plus this value plus other values. So in this second value I have an input cos omega t that is actually multiplied by alpha 1a, which is kind of enhancing its value. So imagine cos omega t is a standard sine wave, and if we if we pass it from an amplifier, then it is actually a y of t. Y of t means output signal. It's a multiplication of a DC, an addition of a DC on top of my input signal cos omega t multiplied by alpha 1a, that is amplification factor. So I will get an output sine wave if having an amplitude of alpha 1a. So this is actually alpha 1a. So that's kind of an amplification factor. Only if this value is small or negligible or ignorable. So what this value exactly is, alpha 3 is the constant that I have pushed forward with my cos cube omega t. A3 is also the constant with cos omega cube of t. So this is kind of like the factor that is involved with the cubed value of my signal. So if alpha 1 is much greater than all other factors that contain a, then the small signal gain is equal to alpha 1a. However, as the signal amplitude increases, becomes a large signal, the gain begins to vary. So if I have only alpha 1 factor multiplied by cos omega t, then everything will be fine. But as our other signals will start to increase, then we will have uh, a discrepancy in the gain, that what we were expecting, we will not get what we were expecting exactly. Therefore, nonlinearity can be viewed as variation of the small signal gain with the input level, and this is evident from the term. So this is exactly what we talked about here. Other terms exist representing signals that were not present in the input signal. So input signal is only cos omega t, but all the other factors that are kind of multiplying by it are coming from other parts. So in the previous equation, our a alpha 2 a square over 2 is DC term that we said it's here. This term is actually the main signal multiplied by an amplification factor. Second harmonic is a2 or alpha 2 a square over 2 cos 2 omega t from the previous equation, and then a3 alpha 3 a cube over 4 cos 3 omega t, that is third harmonic. Harmonics means linear multiplication of fundamental frequency. So imagine if I have an omega that is actually 2 pi f, then this, and if I draw a spectrum of this particular equation, then I will have uh, a frequency value on frequency spectrum. 2 omega means 2 into 2 pi f, that is another frequency spectrum at 2 times f. So for example, my first f is 1 megahertz, then my 2 times omega would be 2 megahertz multiplied by 2 pi, of course. So in most circuits of interest, the output is a compressive or saturating function of input. That is, the gain approaches to zero for sufficiently high input level. So again, we can kind of visualize this impact using a simple V in and V out curve. So imagine we have V in and V out curve, in which we have, for given value of V in, we have a gain multiplication or a gain enhancement multiplied by V in, giving us a V out. We have another point in which our V in will give us a particular V out, and so on. At one point, what will happen, that if I increase my V in, the expected V out is not as I was expecting. So it means that now my gain has reached a saturation point, and after that it will kind of saturate. So if I plot this curve, then it should follow a path like this. So this point was, so my expected line of linear gain enhancement is this dotted line, while my actual line is the blue one. So this area represent saturation point. Sorry, I'll change the color just to make it clear. Yeah, this occurs only if alpha 3 is less than 0, which will make my expression inside the bracket, that is alpha 1 plus 3 alpha 3 a square over 4, less. So what happens when this whole value is let me change the color of my pen. If this value is negligible, then what happens is, for any input V in, my output is only a linear multiplication of alpha 1 into my input, giving me an output or an amplified version of output. Again, for a value of input, the output is actually a linear multiplication of V in. So it's actually V out is almost equal to alpha 1 V in till the point from here till here. But after this point, what happens is my actual expected output is alpha 1 V in that I should get here, but because this A3 is a negative number, it will decrease this overall value and it will drop my point from this to this, and afterwards all the points, all the inputs, all the output that I will receive will not be a linear gain multiplication of my input, and I can say that my amplifier has now reached a saturation point. In RF circuits, this effect is quantified by 1 dB compression point, defined by the input signal level that causes the small signal gain to drop by 1 dB. Now this definition is extremely important for all of high frequency systems, amplifiers, mixers, and so on and so forth. So gain compression, if plotted on a log scale as a function of input level, the output level falls below its ideal value by 1 dB at 1 dB compression point. The 1 dB compression point is usually specified as an upper limit of usefulness of linear operation. So this is my desired. So here I am, or what I am doing is I am taking 20 log A in and 20 log A out, and I'm just trying to plot my desired output. So the gain value here, for example, at this point, for a given A in, I will have a given A out. At this, for a given A in, I have a linear multiplication of gain multiplied by A in, giving me an A out in dB scale, of course. But afterwards, there will be a discrepancy. So my expected value should be here, but my actual value is kind of here. And if this distance, this gap between these 2 points is 1 dB, then I will call this as 1 dB compression point, and I will record my A1 dB here. So what I can define, so for example, imagine I am devising a receiver for radio transmission from somewhere else. So I am taking a low noise amplifier LNA, and if I test that my LNA has 1 dB compression point at an input level of say 10 dB, then I would define all my power levels of my device based upon this 10 dB maximum threshold, because I know that if I increase the input power of my receiver or my transmitter more than this 10 dB value, then my amplifier will enter into a non-linear realm and I will not have any control of gain, and my expected output will not be my output will not be as what I was expecting. So that's why in every data sheet of amplifiers and mixers, we normally have 1 dB compression points, and these 1 dB compression points actually define the upper limit, upper power limit of the functionality of our devices. To calculate 1 dB compression point, we know this equation. This is the DC term. This is the term we have been talking about in last two to three slides, because it is actually multiplied by a standard cosine wave that is an input, and then second harmonics and the third harmonics and their respective amplitudes. The 1 dB compression point is the point where the total coefficient of cos omega t, that is this one, is 1 dB below the linear portion of that same coefficient. So here cos omega t refers to fundamental frequency, that is the original signal at the input. The coefficient of this term refers to the gain affecting the original signal. So actually alpha 1 a plus 3 alpha cube a cube alpha 3 a cube over 4 in whole bracket is actually my gain value. So 1 dB compression point can be mathematically written as 20 log a1 alpha 1a plus the magnitude of 3 alpha cube alpha 3 a cube over 4 is equal to 20 log alpha 1a. That is what my expected outcome of the amplifier should be, that is linear component of the coefficient minus 1 dB. So if this total coefficient is actually a 1 dB below my linear component of the coefficient, then this expression can be written as the expression for 1 dB compression point. So I hope you understand this point, and we will discuss further during our lectures as well, the face-to-face lectures as well. So what value of A corresponds to 1 dB compression point? In the voltage sense, 20 log A1 alpha 1A plus the magnitude of 3 alpha 3A cube over 4 is equal to 20 log alpha 1A minus 1 dB. So here I am doing a little bit of maths. I am pulling these logs formation to one side of the equation and putting the other values on the other side of equation. So I end up with this expression after doing a little bit of maths. That is 0.05 dB is equal to log, and inside the bracket 4 alpha 1a 1 dB compression point, because now this a is my a for 1 dB compression point, divided by 4 alpha 1a 1 dB compression point plus magnitude of 3 alpha 3 a cube of 1 dB compression point. Taking anti-log on both sides, I will eventually end up in 10 power 0.05, and this whole bracket form will be outside the logarithmic terms. And if I do a little bit of maths, then I will end up in an equation in which okay, let's first derive it. So first I will just pull this denominator value here multiplied by 10 into 0.05, and then what I will do, I will cancel these three values, so only this cube will stay square and rest of two a1 dB compression points will cancel out with each other. So now if I multiplied this 4a into 10 is power 4a multiplied by 10 power 0.05 and 4 alpha 1, I pull them in this side of the equation and keep this term, that is inside my my magnitude or my amplitude remaining here. Then what will eventually I get is a 1 dB squared is 0.145 into a1 divided by alpha 1 divided by magnitude of alpha 3, which will eventually give me this value. Now a3 can be a negative number, alpha 3 can be a negative number, because we know that to bring down the gain from expected to the real value, alpha 3 can be a negative value. So that's why we are taking a magnitude here. So I end up with an expression of 1 dB compression point, and we have derived it from a standard yt, that is equivalent to alpha 1 x of t plus alpha 2 x square of t plus alpha 3 and x cube of t, and so on. But rest of the term we have just we are not using them.